Welcome to Lecture 21, in which we will continue to talk about Example 4, which was introduced at the end of Lecture 20. I'm afraid, once again, this is a bit of an involved lecture, and I'm certainly going to try to get away from that with these lectures with quite so many details. But anyway, this one is another one of that case, and so I've written it out in advance. But let me read this with you and help explain what's going on. So in Example 4, at the end of Lecture 20, we began a search for a unitary transformation that would send 0, 0 to square root of 1/10, 0, 0, plus square root of 2/10, 0, 1, plus square root of 3/10, 1, 1, plus square root of 4/10, 1, 0. And we didn't care what effect the transformation had on any other state as long as it was unitary. So we decided to try to implement the following transformation. And here we have completely defined U4, not only its action on the state 0, 0, but also its action on the other states. And so with that definition, the matrix for U4 relative now to the basis given in this order, 0, 0, 0, 1, 1, 1, 1, 0. So keep in mind now that we're working with the basis in that order. Then the matrix relative to that basis would be this. And let me go ahead and say now that for all the matrices in this lecture, they will be relative to this basis in this order. Okay. So now I make a comment. While it is indeed possible to write this unitary matrix as the product of two-level unitary matrices, the procedure is rather tedious, as we will now see. So after considering this approach, we will discuss another technique, and that technique actually will be discussed. In fact, by the time you watch this lecture, you will have already thought about it, because it will be in the last problem on test 20, and yes, last problem on test 20, and then it will also be discussed in lecture 22 at greater length. Okay. So, but now we're going to do the more tedious problem of writing this rather general. It's not a completely general unitary matrix, but this is a rather general unitary matrix, and we're going to see it's certainly not a two-level unitary matrix, but we're going to learn an algorithm now for writing this as a product of two-level unitary matrices. So the first step now, the approach for writing a general unitary matrix as a product of two-level unitary matrices. The idea here is that there are 6 terms below the main diagonal. So here is our matrix, and of course the main diagonal is this. And since, well, you can count 1, 2, 3, 4, 5, 6 terms below the main diagonal. So we need to find 6 or fewer two-level unitary matrices, x1, x2, x3, x4, x5, and x6, such that x6 times x5 times x4 times x3 times x2 times x1 times this matrix U. Actually, I have used the symbol U here to represent U4, and since I've done that throughout the rest of the lecture, I'm not going to go and change it. Just keep in mind that U here represents U4. Actually, yes, let's just stick with that. So U represents U4. Okay, so this is the idea, and the reason that would be convenient is that if we can find matrices x1 through x6 that satisfy this, then using the fact that each one of these is also unitary, we could just multiply out and find that u is equal to the adjoint of x1 times adjoint of x2 times adjoint of x3 times adjoint of x4 adjoint of x5 adjoint of x6. So if we can just find this, then it would be very simple. But how do we find these matrices? Okay, well, here is U4, and it has all these radicals in it. And so the first step, because I wanted to do this work, it's certainly too tedious to do it completely by hand. So here I've plugged the matrix into MATLAB. And I ask, how do we find the X matrices? Well, the idea is this. Suppose that W is a unitary matrix, so W is like U here, and that we use Wij to denote the term in the ith row and jth column of W. Now suppose that Wi0 J0 is non-zero and below the main diagonal of W. Then let X be equal to the identity matrix everywhere except as follows. So all of X will be the identity matrix except for in these four terms. X of J0 J0 will be the complex conjugate of W J0 J0 over the square root of the magnitude squared of W J0 J0 plus the magnitude squared of Wi0 J0. X J0 I0 will be the complex conjugate of Wi0 J0 over the square root of the magnitude squared of W J0 J0 plus the magnitude squared of Wi0 J0, and so on. You can read all of these formulas. Now, using those formulas, we can note the following. Then X is, since X is equal to the identity matrix everywhere except for these four entries, we find that X is a two-level unitary matrix, and not only that, but if we multiply out X times W, we'll find out, well, X times W will also be unitary, and it will have a zero in the I0 J0 position. So this is our idea for how we find these matrices x6, x5, x4, x3, x2, and x1, so that when we multiply all of them times u, we get I. We just go one step at a time. We will eliminate non-zero terms below the main diagonal in the same order we would use for Gaussian elimination. That is, we will go from top to bottom and left to right. So top to bottom and then left to right. I'm using this wiggly line to denote that. And if in following this order you encounter a term that is already zero, you can skip it. The formulas above, if you use these formulas, those formulas would give you that X is equal to I for that step anyway. So you don't have to really calculate I for that step. And that's important to know for your, well, I'll just leave it. Let's just say, though, that you can skip that step. Okay, so in the case we're considering here, the first non-zero term is U21. Here's our matrix U down here. And you see that when we begin to look below the main diagonal, we're going to look top to bottom and left to right. The very first one we encounter, 0.4472, is non-zero. So U21 is the first non-zero term. And so we're going to let X1 be the identity matrix everywhere except for these four entries. Now, you can look at the formulas if you wish, but I can show you a little bit easier way to do this. Okay, first of all, let's note that since all the numbers here are real, then we don't have to worry about these complex conjugates in the first two formulas. Okay, so x11 and x12 here In other words, these first two entries of x1, what are they? Well, we look at u, and if we take this number, 0.3162, and divide it by the square root of the sum of the square magnitudes of these two numbers, that will be this number, x1. And what is this number? It is 0.4472 divided by the square root of the sums of these two magnitudes. So that's how we get this. Then the rest of it is 0 here, and notice that in the next row, this number is that one, and this number is simply the negative of that one. And it's just that easy. So all you have to calculate for each of these X matrices, all you really need to calculate is just two numbers, and then you'll get two other numbers from it, so that you'll have four terms that are neither equal to 0 nor 1, and then everything else in the matrix will be equal to 0 or 1. So that's x1, and notice that if we multiply x1 times u, this is what we will get, and like magic, indeed, we have obtained a 0 here in the 2, 1 term. Let me remind you, this was our original u, and notice it didn't have any zeros at all. But when we multiply that u, when we pre-multiply it by this x1, which you can verify, this is a two-level unitary matrix. When we pre-multiply this u by this x1, we will get this matrix, which you can verify is also a unitary matrix, but now we have a 0 in the 2, 1 term. Okay. And that's what's said here. By comparing x1 times u with u itself, we see that multiplication of u by x1 has given us a product matrix whose 2, 1 term is 0, as desired. Now we look at x1 times u and see that we next want to eliminate the 3, 1 term. So now I0 is 3 and J0 is 1. In other words, now we want to come down here and eliminate this 0.5477. So we will take, for the first entry of x2, it's equal to this 0.5477 divided by the square root of the magnitude squared of that plus the magnitude squared of that. This entry in x2 is equal to this 0.5477 divided by the square root of the sum of the magnitude squared of this plus the magnitude squared of that. And then, and of course, those two are the same. So as before, then we have this number, and then this one is equal to that, and this one are negative of each other. So this would be x2, and x2 times x1 times xu, and voila, again, now we've introduced another 0. So now we want to get rid of the 0.6325, and you'll just read this with you. Now we look at x2 times x1 times u, and we see that the 4, 1 term is next. Then it will be the 3, 2 term of x3 times x2 times x1 times u that we will look at. And then the 4, 2 term of x4 times x3 times x2 times x1 times u. And then the 4, 3 term of x5 times x4 times x3 times x2 times x1 times u. And so if we do all of that, here are the matrices that we will get. So here would be x3, and when we multiply x3 times x2 times x1 times u, now you see that all three of the terms below the diagonal in the first column have gone to 0. And notice, like magic, it's really not an accident. The term in the diagonal has gone to 1. Why do I say it's not an accident? Well, remember that for a unitary matrix, that each row and each row and each column must have a magnitude of 1. And so if we've zeroed out everything else, then the remaining number must be 1. And so now we'll go to the next number below the main diagonal, which is this minus 0.4472 in the third row and second column. And so this will be our x4, and notice that now that term goes to 0. Now we'll try to get rid of this number, the 0.7071. And so this would be the next, here's the next x matrix, multiply it, and we get this, which you can see now has a 0 there. And now we're down, we only have one remaining term below the main diagonal that is non-zero. And notice that when we zeroed out this term, we also got another 1 here in the diagonal. Okay, now when we follow the same formulas as above to find x6, this is what we get. And when we multiply x6 by x5 times x4 times x3 times x2 times x1 times u, notice what we get. It's not quite the identity matrix. In fact, it is the identity matrix in every entry except for the last entry, and here where we want a 1, instead we have -1. And so we say, notice how we have not quite obtained the desired value of I on the final step. This kind of problem can only arise on the calculation of the last X matrix. Now, when I say the last X matrix, I'm going to, well, I guess I'm going to say it here, so I'll just wait. To avoid this problem, simply let your last X matrix be the conjugate transpose of the matrix xn minus 1 times xn minus 2 times ... times x2 times x1 times u. And here's the remark I was about to make. Note that the last X matrix is the one you calculate when there are only four terms left that are neither diagonal ones nor off-diagonal zeros. As you will see in the first problem below, it is not always the matrix corresponding to an elimination of the term in the last row and next to last column. So in other words, right now, this is our last X. And it does indeed correspond to the elimination of this term here, which is in the last row and next to last column. But that won't always be the case. That number might already be zeroed out from a previous step, or who knows, maybe even from the very beginning of the problem. And in that case, then your last X calculated might be corresponding to some other entry. Let's look at your homework problem. See, in the first homework problem, I'm going to ask you to use this procedure to decompose this matrix into two-level unitary matrices. And this number here is already 0, and when you go through this procedure, that will not change. So the last X that you calculate, in fact, I'm go ahead and tell you now, you only have to calculate 2 matrices. And so the first one you will calculate will be to get rid of this square root of 3/5. And then the next one that you calculate will be to get rid of this negative square root of 3/5. And that will be the one that you calculate to get rid of this. That'll be your last matrix. So it will not correspond to the elimination of the term here in the last row and next to last column. So just keep that in mind. But anyway, to avoid this problem, simply let your last X be the conjugate transpose of the matrix xn minus 1, xn minus 2, x2, x1, u. So here you see we have the n here is 6, and so n minus 1 is 5, 4, 3, 2, 1, u. So you can see that we've just taken this matrix here. This x6 is not good. It doesn't work. Instead, let's take, and you can see actually if you compare this matrix here with X6, X6 is not the conjugate transpose of this matrix. But that's what we really want for X6. And in fact, let me say one other thing. You don't even have to calculate your last X to see whether there's a problem or not. Just always go with the rule that your final X, the final X that you need, when you only have 4 terms left that are neither 0 nor 1, neither off-diagonal zeros or diagonal 1s, when you only have 4 such terms left, then your last matrix will simply be the conjugate transpose of this matrix you've obtained up to that point. And so that is what we use here for X6. You can verify that that's the conjugate transpose of this matrix. And when we multiply that matrix, that X6 times X5 times X4 times X3 times X2 times X1 times U, we do indeed now get the identity matrix. And one note here for you, I say, notice that here and below I have used the transpose command from MATLAB rather than taking the conjugate transpose. This is permissible because these are all real matrices. Otherwise, be sure to use the conjugate transpose. And so finally, what we get, remember, once we get now X6 times X5 times X4 times X3 times X2 times X1 times U is equal to the identity matrix, then we can say, okay, U is equal to the transpose of X1, actually conjugate transpose. So conjugate transpose of X1 times the conjugate transpose of X2 times the conjugate transpose of X3 times the conjugate transpose of X4 times the conjugate transpose of X5 times the conjugate transpose of X6. And if we multiply those together, we get this matrix, which we see does indeed match the matrix U that we started with. So this is the procedure for writing an arbitrary unitary matrix in terms of 2-level unitary matrices. So we've accomplished our goal of writing U as a product of 2-level unitary matrices, so we could now easily implement U because we know how to find the circuit for any 2-level unitary transformation. So now for the problems, and I've already said a little bit about problem 21.1. Here's our matrix U, and I've put a lot of zeros there so that this will be very quick for you. Don't worry that this is going to take forever. It won't. So we want to write this U as the product of 2-level unitary matrices. I'm telling you in advance, you're only going to need 2 matrices, not 6, just 2, using the procedure above. That is, U is equal to AB, where A and B are obtained using the procedure shown. And I'm asking you simply, what is A? What is that first matrix? I hope that you will also find B, and be careful now, you need to use the note above about how to find the last matrix. So I hope that you also find B, and then we'll verify that A times B is equal to U. But I'm not asking you to do all that, at least not yet. I don't promise that I won't do it later, but not right now. So all I'm asking you to do is find A. And here are the 4 choices. And then for 21.2, I'm asking this problem. Okay, we have this circuit shown here where we have 2 controlled gates. Here we have the this setup, which means that this is not activated unless the second qubit is 0, and this one is not activated, or when I say not activated, I mean it doesn't affect the first qubit. So this will not affect the first qubit unless the second qubit is 0, and this one will not affect the second qubit unless the first qubit is 0. Now here is how these gates U1 and U2 can affect qubits when they're activated. U1 of 0 is A0 plus B1. U1 of 1 is B0 minus A1. U2 of 0 is C0 plus D1, and U2 of 1 is minus D0 plus C1. And so for this circuit, I ask you find the matrix using the standard basis for the following circuit. And so here's the circuit. Again, you want the matrix relative to the standard basis. And so here are your 4 choices. And that concludes Lecture 21. I hope that these problems, again, 21.1 will not be very time consuming, but I hope that you will find B as well and verify that your A that you obtain times B gives you this matrix U. But that's it for these problems and for this lecture, so good luck.